Over the years, I've worked with mercury many times, and it's almost always a bit of a pain because it requires special handling as well as waste management. But despite this, I think it's still slowly becoming one of my favorite elements. The thing that I find most interesting about it is its ability to form alloys with most other metals at relatively low temperatures. This process is generally known as amalgamation, and it often leads to some really interesting and sometimes weird-looking interactions. I've already kind of covered this a bit in previous videos for gold and aluminum, but for most other metals, there's very little information. There are also pretty much no photos or videos to even see what their amalgams look like, and my goal is to try to combine mercury with as many different metals as possible. For this video, I've decided to try it with sodium metal. Sodium metal is a highly reactive element, and it especially likes to react with things like oxygen and water. So when storing it, it's usually kept under a layer of an inert solvent like mineral oil to help protect it from air and moisture. Before I could even try and combine it with mercury, I had to first take some of it out of this jar and remove the oil. Then using some more paper towel, I tried to get rid of as much mineral oil as possible. At this point, it would probably be okay to use, but I wanted to really make sure that all the oil was gone. So I transferred it to a small beaker and I poured in some toluene. This solvent will dissolve any oil that remains, but unlike the oil, it easily evaporates. Before this, I had never made any sodium amalgam before, but based on what I had read online, I knew that the reaction could be quite violent. Sodium's a relatively soft metal, so this was pretty easy to do just using a knife. On the inside, it was all still fresh sodium, so it was initially nice and shiny. However, it almost immediately started reacting with moisture and oxygen, and it started to tarnish. I wanted to prevent this as much as possible, so I cut the sodium as fast as I could, and when I was done with each piece, I immediately dropped it back into the toluene. In this shot, I only showed me cutting one of these really small pieces, but I ended up cutting most of the sodium down to around this size. Now it was time to set up the mercury side of things. This reaction was apparently notorious for a lot of splashing, as well as flaming sodium. To deal with this, some procedures suggested just using a really large flask, but they were also doing it on a much larger scale. I figured that because I was only doing this with a few milliliters of mercury, a large test tube would probably be fine. So I poured in a random small amount of mercury, and then I pulled out my small piece of sodium, quickly dried it, and threw it in. I was kind of nervous that I'd immediately get fire in molten sodium, but nothing happened. The major reason for this seemed to be that the sodium was just a bit too tarnished, and it prevented it from coming into contact with the mercury. The sodium's also way less dense than the mercury, so it kind of just floated on top, which didn't really help either. To fix this, according to some procedures that I read, it's pretty common to use something like a glass rod and to shove the sodium into the mercury. Then once it's underneath, it can be scraped and crushed to expose the fresh sodium. So I decided to try this, and initially I still had some trouble getting it started, but then suddenly there was a little thump, and all the sodium instantly disappeared. Then when I mixed it around a bit, I noticed that the texture of the mercury had also changed. I then continued adding more sodium, but even the next one didn't result in any fire or sparks. On my third run though, I used a slightly bigger piece of sodium, and I managed to get some fire. I couldn't find a good reference for exactly what was going on here, but then again, I don't think it's too complicated. As the amalgam forms, it generates a lot of heat, which quickly causes all the sodium to melt. This increase in temperature and surface area causes the sodium to react even faster, which in turn generates even more heat, and it creates a positive feedback loop. As I continued adding more sodium, I started getting a lot of solid chunks that wouldn't disappear. This told me that the overall concentration of sodium was now probably getting above 2%. And at this point, I had run out of small pieces of sodium to add, so I went to cut some more. However, when I came back only a few minutes later, the entire thing had solidified. I thought that maybe it had just cooled down a bit, so I tried seeing if I could melt it using my heat gun. However, even after shooting it at max heat for over a minute, it was still completely solid. I then let it cool to room temperature and hoped that maybe it would shrink a bit so I could knock it out of the tube. But that didn't turn out to be the case, and I just had to smash it. It ended up coming out as almost a completely intact chunk, and the glass also didn't end up sticking to it at all. I then collected the large piece and anything else that I could get without pulling glass along with it. The amalgam didn't feel very strong, and I felt that dropping it just like a centimeter would be enough to break it. But that apparently wasn't the case, and to break it, I just ended up pushing on it a bit. Anyway, several minutes later, I moved on to store the amalgam, and it had already started to tarnish. I wanted to prevent it from degrading even more, so after everything was added to the vial, I flushed it with some nitrogen. This was my final result, which I thought was pretty interesting. What I thought was really cool was that just by adding a small amount of sodium, I was able to completely solidify the mercury enough to crush it into powder. Okay, so now that I had made the solid amalgam, I really wanted to try directly making it in its liquid form. And on top of this, I also wanted to try making the amalgam on a larger scale. So I weighed out 100 grams of mercury and 1 gram of sodium metal. The reason I chose this ratio was because, as I mentioned before, when the concentration of sodium is at or below 1%, it's able to stay as a liquid. This time, I got fire with every piece that I added, and I think it was because the mercury was just more spread out and the sodium pieces were larger. And although this is something that I wanted to happen before, it kind of wasn't ideal now. All the sodium that burns just represents a loss, and on top of this, the oxides that form contaminate my amalgam. So besides safety reasons, this is why most of the time when people make this, they first do something to protect it from oxygen. And one of the simplest ways to do this is to just replace all of the air with nitrogen. To demonstrate this, and so that you could actually see what was going on, I transferred everything into a clean flask. Then I lowered in my tube that was connected to my nitrogen tank, and I pushed out all of the air. Now to test this out, I lowered in a somewhat large piece of sodium, and, well, there was no fire. It still popped and fizzled like the other times, but it didn't coat the inside of the flask with all those nasty oxidation products. I continued adding the rest of the 1 gram of sodium, and you can see that now, without the oxygen, the process is a lot cleaner and safer. What I thought was cool was how the very last piece reacted. All the other times it happened below the surface of the mercury, so we couldn't really see what was going on. But now it was a lot more clear, and we can see the sodium quickly reacting and causing the mercury around it to solidify. After everything was added, I mixed it around for a few minutes to try and dissolve as many of the solid pieces as possible. And when I felt that it was pretty much all liquid again, I poured it into a vial. Then, like before, once it was all added, I flushed it out with nitrogen. But anyway, this was all still kind of hot from the reaction, so for the moment, I put it somewhere to cool. So now I have the liquid amalgam, but what can this do that the solid one can't? Besides the major difference that one's a solid and the other's a liquid, the only other big difference just comes down to sodium concentration. This will end up affecting how vigorous the reaction is, but in the end, it's still the same reaction. I think the difference in reactivity, though, was highlighted pretty well when I tried adding the liquid one to water. Even after a minute, it really didn't look like much was happening, so to get things started, I added a few drops of acid. Anyway, now on the other hand, in terms of cool and fun chemistry, it is different. This is what happens when a solution of ammonium chloride is added to the liquid form. And this is what happens with the solid one. It's still puffed up just like the liquid one, but the overall visual effect of it was really different.